Cold fusion. Cold fusion entered public consciousness in March 1989, when two electrochemists, Martin Fleischmann and Stanley Pons, announced that they had achieved nuclear fusion at room temperature. Fusion, the process that powers the sun, normally requires immense temperatures and pressures. To claim it could occur inside a tabletop apparatus sounded almost impossible. Yet the announcement was made not through the usual slow channels of peer review, but at a press conference. The promise was enormous. An abundant, clean source of energy, free from radiation risks and fuel scarcity. The experiment itself appeared deceptively simple. Palladium electrodes were submerged in heavy water, and an electric current was passed through the system. According to Pons and Fleischmann, the palladium absorbed deuterium atoms until fusion reactions began occurring within the metal lattice. The key evidence was excess heat, more energy leaving the system than could be accounted for by chemical reactions alone. In some reports, traces of nuclear byproducts were also mentioned, though inconsistently. The reaction from the scientific community was immediate and intense. Laboratories across the world attempted to replicate the experiment. If cold fusion were real, it would be one of the most important discoveries in modern history. Physicists, chemists, and government research institutions redirected resources toward verification. What followed was not confirmation, but confusion. Most replication attempts failed to produce excess heat. Some reported marginal effects, but these varied wildly and lacked consistency. Crucially, the predicted nuclear signatures of fusion, specific radiation patterns and particle emissions, were either absent or far below expected levels. As scrutiny increased, methodological weaknesses became apparent. Measurements of heat output were highly sensitive to calibration errors. Small miscalculations could produce the illusion of surplus energy. As weeks turned into months, confidence eroded. Papers criticizing the original work began to outnumber those supporting it. Theoretical physicists pointed out that the proposed mechanism violated well-established nuclear physics. Fusion inside a metal lattice at such low energies would face enormous barriers that the experiment did not convincingly overcome. By the early 1990s, cold fusion had largely disappeared from mainstream science. Funding dried up, and journals became reluctant to publish further claims. Some researchers continued working in isolation, rebranding the idea under new terms, but reproducible evidence never emerged. The initial excitement gave way to reputational damage, particularly for the scientists involved. Cold fusion did not fail because it was ridiculed, but because it could not be reliably repeated. In science, repetition is not optional. It is the mechanism by which truth separates itself from error. The cold fusion episode remains a defining example of how extraordinary claims demand not just evidence, but evidence that survives independent verification. What began as a revolutionary promise ultimately became a reminder of the discipline required to distinguish discovery from illusion. The M drive. The M drive emerged in the early 2000s as a concept that appeared to challenge one of the most fundamental principles of physics, the conservation of momentum. Proposed by British engineer Roger Scheuer, the device was described as a propulsion system that could generate thrust without expelling propellant. In traditional rocketry, motion is achieved by throwing mass in the opposite direction. The M drive claimed to do something radically different, to push against nothing. The core design of the M drive was deceptively simple. It consisted of a closed, asymmetric metal cavity, wider at one end than the other. Microwaves were injected into the chamber, where they bounced back and forth between the walls. According to Scheuer, the geometry of the cavity caused the electromagnetic waves to exert unequal pressure on its ends, resulting in a net force. Even a tiny force, if real, would be revolutionary for space travel. A propulsion system requiring only electricity could operate continuously, dramatically reducing mission costs and travel times. At first, the idea was met with widespread skepticism. Established physics predicted that any internal forces within a closed system must cancel out. Without ejecting mass or interacting with an external field, thrust should be impossible. For years, the M drive remained largely ignored, circulating on the fringes of engineering discussions and online forums. Interest reignited when small experimental results began to surface. Several independent groups reported detecting minute thrust values, often measured in micronewtons. These forces were barely above the noise threshold of the instruments used to detect them. Nevertheless, the consistency of some measurements drew attention. The possibility that a violation of known physics had slipped through unnoticed was difficult to ignore. The turning point came when a NASA-affiliated laboratory, EagleWorks, published preliminary findings suggesting that the M drive produced measurable thrust in a vacuum chamber. The reported force was extremely small, but the implications were enormous. Media coverage followed quickly, often presenting the device as a potential breakthrough in space propulsion. The distinction between experimental anomaly and confirmed discovery began to blur in public perception. As attention grew, so did scrutiny. Replication attempts expanded, and experimental setups became more sophisticated. Researchers introduced better thermal controls, magnetic shielding, and more precise torsion balances. With each improvement, alternative explanations emerged. Temperature gradients caused by microwave heating could lead to expansion of materials, subtly shifting the apparatus. Interactions between electrical currents and Earth's magnetic field could generate forces unrelated to propulsion. Even air currents within imperfect vacuum chambers became suspect. Gradually, a pattern formed. When experimental controls were tightened, the measured thrust diminished or disappeared entirely. In several cases, reversing the orientation of the device failed to reverse the direction of the supposed thrust, an inconsistency incompatible with genuine propulsion. Some experiments detected forces only when power cables or external equipment were arranged in specific configurations, suggesting that the source lay outside the cavity itself. By the late 2010s, comprehensive studies concluded that the M drive did not produce thrust beyond experimental error. One detailed analysis demonstrated that the observed forces could be fully explained by thermal effects and electromagnetic interactions with the environment. When these variables were eliminated or accounted for, no anomalous thrust remained. The M drive did not collapse in a single moment. Instead, it slowly faded as evidence accumulated against it. What had once appeared as a crack in the foundations of physics resolved into a lesson about measurement at extreme sensitivity. Detecting forces at the micronewton level requires extraordinary precision, and even slight imperfections can create convincing illusions. Despite its failure, the M drive occupies a unique place in scientific history. It illustrates how bold ideas can persist not because they are correct, but because they are intriguing. It also shows how science responds to such ideas, not through dismissal alone, but through careful testing, replication, and eventual resolution. The M drive did not change the laws of physics. It reinforced them, demonstrating once again that reproducibility is not merely a standard, but the boundary between speculation and discovery. N-rays. At the beginning of the 20th century, physics stood at the edge of rapid transformation. X-rays, radioactivity, and new forms of electromagnetic radiation were being discovered in quick succession. In this atmosphere of expectation, the boundaries between careful observation and hopeful interpretation grew thin. It was within this context that N-rays entered scientific history. In 1903, French physicist René Blondlot announced the discovery of a new type of radiation. He named it N-rays after the city of Nancy, where his laboratory was located. According to Blondlot, these rays were emitted by many common materials and could enhance or diminish the brightness of objects under certain conditions. Unlike X-rays, N-rays were not detected by photographic plates or instruments, but by the human eye. Blondlot described experiments in which a barely visible electric spark would become brighter when exposed to N-rays. Observations were made in darkened rooms, often after long periods of visual adaptation. The effects were subtle, fleeting, and required careful attention. Despite this, Blondlot was a respected physicist, and his claims were taken seriously. Soon, other French scientists reported similar observations, confirming the existence of N-rays through comparable visual methods. Within a short time, dozens of papers were published. N-rays were said to pass through aluminum but not lead, to be refracted by prisms, and even to be emitted by the human nervous system. The phenomenon expanded rapidly, acquiring new properties with each report. Yet almost all confirmations came from the same scientific community, using similar experimental techniques and relying heavily on subjective perception. Outside France, the situation was different. Physicists in Germany, Britain, and the United States attempted to reproduce the experiments. They saw nothing. The reported changes in brightness failed to appear, no matter how carefully the procedures were followed. The discrepancy raised quiet concerns, but respect for Blondlot's reputation delayed open criticism. The turning point came when American physicist Robert W. Wood visited Blondlot's laboratory. Wood was known for his skepticism and his skill in experimental design. During a demonstration of N-ray refraction, Wood discreetly removed a critical prism from the apparatus. According to the theory, the effect should have vanished. Blondlot continued the experiment and confidently described the expected visual changes, unaware that the optical component was no longer present. Wood's observations were published soon after. He concluded that N-rays did not exist and that the reported effects were products of suggestion and expectation. Once the possibility of observer bias was openly acknowledged, the phenomenon collapsed rapidly. Scientists who had previously reported N-rays were unable to demonstrate them under controlled or blinded conditions. The disappearance of N-rays was as sudden as their rise. Publications ceased and the scientific community moved on. No physical mechanism was ever identified, and no objective detection method was established. What remained was not a new form of radiation, but a powerful example of how easily perception can be shaped by belief. N-rays did not fail because they contradicted known physics. They failed because they depended on the observer rather than the experiment. The episode revealed a vulnerability in scientific practice at a time when instrumentation was limited and trust in human senses remained high. It also helped accelerate the adoption of stricter experimental controls, including blind testing and objective measurement. Today, N-rays are remembered not as a discovery, but as a warning. They demonstrate that even skilled scientists can mislead themselves when expectations go unchallenged. In the history of irreproducible discoveries, N-rays stand as a quiet reminder that observation alone is never enough. It must be insulated from belief, repetition, and desire. The memory of water. The idea that water might retain a memory of substances once dissolved within it stands among the most controversial claims in modern science. It challenges the foundations of chemistry, biology, and molecular physics, while occupying a fragile space between laboratory research and belief. Unlike many irreproducible discoveries that vanished quickly, the memory of water persisted, resurfacing repeatedly despite repeated failure under controlled conditions. The modern scientific form of this idea emerged in the late 1980s, when French immunologist Jacques Benveniste published experimental results suggesting that highly diluted solutions could still produce biological effects. In these experiments, antibodies diluted far beyond the point where any molecules should remain were reported to trigger responses in immune cells. According to established chemistry, such a result should have been impossible. Yet the reported data appeared statistically significant. At the center of the claim was water itself. Benveniste proposed that water could preserve structural information about substances that had once been present, even after extreme dilution. This concept implied that water possessed a form of molecular organization capable of encoding and transmitting biological signals without physical molecules. The implications were profound, touching not only experimental biology but the very nature of matter. The publication immediately drew attention not only because of its claims, but because it appeared in a leading scientific journal. The editorial decision was unusual, accompanied by an explicit note expressing skepticism and calling for independent verification. Laboratories around the world attempted to replicate the experiments using the same protocols. What followed was a pattern that would define the memory of water controversy. Initial replications sometimes reported weak effects, but these results were inconsistent and unstable. Small changes in experimental conditions caused the effect to vanish. When procedures were tightened and observer bias reduced, the reported biological responses disappeared entirely. To address growing concerns, a supervised replication was organized. Investigators introduced blind testing, ensuring that researchers could not know which samples were supposedly active. Under these conditions, the effects collapsed. The statistical signals that had previously appeared convincing dissolved into random noise. Theoretical explanations offered by supporters failed to gain traction. Proposed mechanisms involving long-range molecular structuring or electromagnetic imprinting conflicted with well-understood properties of liquid water. At the molecular level, hydrogen bonds in water rearrange on timescales measured in trillionths of a second. Any stable, information-rich structure capable of surviving dilution and agitation would contradict decades of physical chemistry. Despite mounting criticism, the idea did not disappear. Instead, it migrated beyond mainstream science. Proponents argued that existing theories were incomplete, that subtle effects were being suppressed by conventional methodology. The failure to reproduce results was framed not as disproof, but as evidence of an elusive phenomenon sensitive to experimental intention and context. Over time, the memory of water became emblematic of a broader problem in experimental science. It highlighted how easily statistical fluctuations, procedural flexibility, and unconscious bias can combine to produce convincing but false results. The case also demonstrated the importance of independent replication as a corrective force, particularly when claims challenge foundational principles. Today, no reproducible evidence supports the existence of water memory as originally proposed. Under controlled, blinded conditions, the effect disappears. What remains is not an unresolved mystery, but a well-documented episode illustrating how extraordinary claims can survive through narrative rather than verification. The memory of water endures as a concept because it appeals to intuition, the idea that substances leave traces, that matter remembers. In science, however, memory requires a mechanism. Without one that withstands repetition and scrutiny, the phenomenon dissolves, leaving behind only the outline of a discovery that could not be reproduced. Polywater. During the Cold War, scientific anxiety often traveled faster than certainty. In the 1960s, as competition between superpowers extended into laboratories, even minor anomalies could escalate into perceived threats. It was in this climate that polywater appeared, not as a bold theory, but as an unsettling observation that slowly grew into a global concern. Polywater was first reported by Soviet scientists who were studying the behavior of water confined within narrow quartz capillaries. Under these conditions, the water seemed to display unusual properties. It appeared thicker than normal water, flowed more slowly, and exhibited an abnormally high boiling point. Most alarming of all, early reports suggested that polywater could convert ordinary water into itself upon contact. The idea of a new form of water with altered molecular structure was both fascinating and disturbing. Water was one of the most thoroughly studied substances in chemistry. If a stable, alternative form existed, it could overturn basic assumptions about hydrogen bonding and molecular interactions. The notion that polywater might spread uncontrollably led to speculation about environmental and biological risks. As news of the discovery spread, laboratories outside the Soviet Union began investigating. Early experiments appeared to confirm some of the reported properties. Measurements indicated higher viscosity and altered surface tension. The scientific community took the possibility seriously, in part because the results seemed modest rather than sensational. Polywater did not promise energy or power. It threatened uncertainty. Theoretical explanations quickly followed. Some proposed that water molecules inside confined spaces formed long polymer-like chains, giving rise to new physical behavior. These models, while speculative, were not immediately dismissed. The limited understanding of water structure under extreme confinement left room for interpretation. However, as research intensified, inconsistencies emerged. The properties of polywater varied significantly between laboratories. Some samples showed dramatic changes, others barely differed from ordinary water. The supposed ability of polywater to transform normal water could not be reliably demonstrated. Reproducibility remained elusive. Closer analysis revealed a critical oversight. The water samples were extraordinarily small, and the capillaries used in experiments were not chemically inert. Trace amounts of contaminants, including sodium, silicon, organic residues, and even biological material, were present. In such tiny volumes, these impurities could dominate the observed behavior. When purification methods improved and contamination was carefully eliminated, polywater lost its distinctive properties. Its viscosity returned to normal. Its boiling point aligned with standard water. The mysterious substance ceased to exist. What had been interpreted as a new phase of matter was revealed to be water altered by microscopic pollution. The realization was sobering. The fear that polywater might represent a spreading threat dissolved as quickly as the phenomenon itself. No new molecular structure had been discovered. Instead, polywater became an example of how experimental artifacts can masquerade as fundamental discoveries. Polywater did not vanish in disgrace. Rather, it quietly retreated as evidence accumulated. The episode reinforced the importance of purity, control, and skepticism in experimental chemistry. It also highlighted the psychological pressure under which scientists operate, especially when working at the limits of measurement. Today, polywater is remembered not for what it was, but for what it taught. Even the most familiar substances can behave unpredictably under imperfect conditions. Without reproducibility, even well-intentioned observations can crystallize into illusions. Polywater stands as a reminder that in science, the smallest contaminants can produce the largest misunderstandings. The wow signal. On the night of August 15, 1977, a quiet anomaly entered the history of astronomy. It did not arrive with light, motion, or sound, but as a sudden spike in radio intensity detected by a stationary radio telescope known as Big Ear. The instrument, operated by Ohio State University, was part of a long-running survey searching for narrowband radio signals that might indicate extraterrestrial intelligence. For years, the telescope had recorded nothing but noise, pulsars, and the familiar background of the universe. The signal appeared without warning. It rose sharply above the background radiation and remained strong for 72 seconds, the exact amount of time it would take a distant source to pass through the telescope's fixed field of view as Earth rotated. The frequency was exceptionally narrow, centered near the hydrogen line, a region of the radio spectrum long considered significant in the search for intelligent signals due to hydrogen's abundance in the universe. Days later, astronomer Jerry R. Emmon was reviewing pages of computer printouts when he noticed the unusual sequence of characters representing the signal's intensity. Next to it, he wrote a single word in red ink, "Wow!" The name would remain. The characteristics of the signal were immediately striking. It did not resemble known astrophysical phenomena. It was too strong, too narrow, and too clean. Natural sources typically produce broader emissions or repeat over time. Human-made interference was also considered, but no satellites or transmissions were known to operate at that frequency, and the signal did not match patterns associated with terrestrial noise. Yet the most unsettling feature was its isolation. The signal never appeared again. Big Ear returned to the same region of the sky repeatedly, but the anomaly was never detected a second time. Other radio observatories found nothing. Without repetition, the signal remained suspended between explanation and speculation. Over the years, numerous hypotheses were proposed. Some suggested it originated from a distant star system. Others pointed to rare cosmic events or reflections from space debris. Each explanation addressed certain aspects of the signal while failing to account for others. None could be confirmed without additional data. As time passed, the wow signal became less a single event and more a symbol. It represented the challenge of interpreting a universe observed through incomplete instruments and fleeting moments. In radio astronomy, confirmation depends on recurrence. A signal seen once cannot be verified, no matter how compelling its properties appear. Advances in technology expanded the search. More sensitive telescopes scanned wider portions of the sky with greater resolution. Vast datasets accumulated. Still, no signal matching the original characteristics was detected. The absence of repetition gradually shifted the signal's status from potential discovery to unresolved anomaly. Unlike many irreproducible findings, the wow signal was never disproven. There was no experimental error to correct, no contamination to remove, no cable to replace. The data remained exactly as recorded. What was missing was context, the ability to see the event again. The signal's endurance in scientific memory reflects its ambiguity. It neither confirmed the existence of extraterrestrial intelligence nor ruled it out. Instead, it highlighted the limits of observation. A single measurement, no matter how precise, cannot stand alone. Today, the wow signal occupies a quiet place in scientific history. It is not evidence, nor is it illusion. It is a reminder that discovery requires more than detection. Without reproducibility, even the most intriguing signals fade into uncertainty, leaving behind a brief mark on paper and a word written in ink. Hutchison Effect. The Hutchison Effect emerged not from a university laboratory or government research facility, but from a private apartment filled with improvised equipment. In the late 1970s and early 1980s, Canadian inventor John Hutchison claimed that complex electromagnetic fields could produce dramatic physical anomalies. According to his reports, ordinary materials behaved in ways that appeared to defy gravity, thermodynamics, and classical mechanics. Hutchison described a setup involving a combination of radio frequency generators, Tesla coils, Van de Graaff generators, and powerful electromagnets. When these devices operated simultaneously, he claimed, objects within the field would levitate, metals would fuse without heat, and materials would fracture or bend without applied force. Photographs and videos circulated, showing strange distortions and fragmented objects. The visual nature of the claims drew attention. Unlike abstract measurements, the Hutchison effect appeared to produce observable transformations. Pieces of metal seemed partially melted and twisted. Heavy objects appeared suspended in midair. The idea that electromagnetic fields alone could manipulate matter so dramatically captured public imagination. Attempts to reproduce the effect quickly followed. Researchers and engineers sought to recreate Hutchison's experimental conditions. However, the descriptions provided were vague and inconsistent. Critical parameters such as field strength, frequency, timing, and spatial configuration were not clearly defined. Hutchison himself stated that the effect occurred spontaneously and could not be reliably controlled. This lack of repeatability became central. Without stable conditions, no independent laboratory could generate the reported anomalies. In some cases, similar setups produced nothing unusual. In others, damage to equipment occurred, but without the claimed effects. The phenomenon appeared tied to Hutchison's personal environment rather than the apparatus itself. Skeptical explanations accumulated. Critics suggested that the visual effects resulted from mechanical stress, electrical arcing, or chemical reactions. Some materials shown in photographs were consistent with known forms of metal fatigue or exposure to high voltage. The levitation effects, when examined carefully, lacked clear evidence of sustained force and could be attributed to momentary impulses or staged conditions. Despite these critiques, the Hutchison effect resisted definitive disproof because it resisted definition. There was no formal experimental protocol to test, no equations to falsify, and no measurable outputs to verify. The effect existed as a collection of demonstrations rather than a reproducible process. Over time, interest waned. Scientific institutions require stability and repetition, and the Hutchison effect offered neither. Without controlled experiments, peer-reviewed publications, or consistent results, it remained outside the boundaries of accepted research. The Hutchison effect occupies an unusual position among irreproducible discoveries. It was not a statistical anomaly or a measurement error. It was a spectacle, compelling in appearance, but empty in structure. Its failure was not due to a single flaw, but to the absence of a foundation upon which verification could stand. In the end, the Hutchison effect did not collapse under scrutiny. It dissolved under the weight of irrelevance. Without reproducibility, even the most striking phenomena fade into obscurity. What remains is a lesson in the difference between seeing something happen and knowing why it happens. Science demands not only observation, but repetition, control, and explanation. The Hutchison effect offered none of these, and in doing so defined its own limits. The Starch, Iodine, disappearing reaction. Among the many scientific anomalies that briefly puzzled researchers, the Starch, Iodine disappearing reaction stands out for its quiet simplicity. There was no grand theory behind it, no promise of revolution. Instead, It appeared as a small inconsistency in a familiar chemical process, observed and described long before modern instrumentation brought precision to laboratory work. Its mystery grew not from spectacle, but from uncertainty. The reaction itself was well known. When iodine is added to a starch solution, it produces a deep blue color, a result of iodine molecules interacting with the helical structure of starch. This reaction was widely used as an indicator in chemistry and biology classrooms. Its behavior was expected, reliable, and easily demonstrated. And yet, early experimental reports described something unusual. In certain conditions, the blue color was said to fade unexpectedly, sometimes disappearing entirely, only to return later without further intervention. The timing of this disappearance varied, as did the intensity of the color change. Some researchers reported that the reaction behaved differently depending on lighting, agitation, or even the order in which components were mixed. These inconsistencies suggested that the reaction was not as stable as once believed. Because the reaction relied on visual observation, interpretation played a significant role. Color perception is influenced by contrast, ambient light, and observer expectation. In early laboratories, where standardized lighting and precise measurement tools were rare, such variables often went unnoticed. The reaction appeared unpredictable not because it was anomalous, but because its conditions were poorly constrained. As interest grew, attempts to reproduce the disappearing effect yielded mixed results. Some laboratories observed faint changes in color intensity, while others saw none at all. Reports conflicted, creating a fragmented picture. Without a consistent framework for replication, the phenomenon remained ambiguous. Gradually, more careful studies began to clarify the situation. Researchers examined the influence of temperature, iodine concentration, starch purity, and the presence of reducing agents. It became clear that iodine could be chemically altered during the reaction, especially in the presence of contaminants or reactive substances. These changes affected the visible color without altering the underlying chemistry. Oxygen exposure, pH variation, and trace impurities all contributed to shifts in reaction behavior. When these factors were controlled, the reaction behaved consistently. The disappearing color was not a mysterious transformation, but a predictable outcome of chemical interactions that had previously gone unrecognized. As methodology improved, the reaction lost its reputation for unpredictability. What had once seemed unstable was revealed to be sensitive. The phenomenon did not vanish because it was disproven, but because it was understood. The conditions that produced the disappearing effect could be explained and managed, eliminating the illusion of inconsistency. The starch-iodine reaction illustrates a subtle category of irreproducibility. The early reports were not fraudulent, nor were they entirely incorrect. They were incomplete. Without sufficient control, ordinary chemical behavior can appear erratic, inviting speculation where none is needed. In the end, the reaction returned to its place as a teaching tool rather than a mystery. Its brief period of uncertainty serves as a reminder that reproducibility depends not only on repeating an experiment, but on understanding every variable within it. When observation outpaces explanation, even the simplest reactions can appear to defy reason. Once understanding catches up, the mystery quietly dissolves. Cold reading psychic experiments. Cold reading entered scientific attention not as a single experiment, but as a pattern repeatedly mistaken for evidence of psychic ability. For decades, individuals claiming extrasensory perception demonstrated an apparent ability to extract detailed personal information from strangers. Names, life events, emotional struggles, and even medical conditions were described with striking confidence. To observers, the accuracy seemed extraordinary. Early experimental attempts to evaluate these claims were often informal. Demonstrations were conducted in public settings, television studios, or loosely controlled laboratory environments. Psychics appeared to deliver highly specific statements that resonated deeply with their subjects. When recorded and reviewed, sessions often seemed to show a remarkable alignment between the reader's statements and the subject's personal history. This apparent precision attracted scientific interest. Researchers sought to determine whether these abilities represented genuine anomalous cognition or an unknown psychological mechanism. Initial studies reported success rates higher than chance. Subjects frequently rated readings as accurate, emotionally meaningful, and personally revealing. However, closer examination revealed a critical factor: interaction. Cold reading relies on subtle feedback, verbal affirmations, facial expressions, body language, and emotional cues. Even silence can serve as information. Readers begin with broad, high-probability statements and refine them in response to microreactions. Over time, these refinements create the illusion of specificity. When experiments were redesigned to reduce feedback, the effect weakened. Subjects were instructed to remain neutral. Readers were prevented from seeing or hearing reactions. In some cases, readings were delivered through written text without direct interaction. Under these conditions, accuracy ratings dropped sharply. Further controls introduced blind protocols. Readers were given no information about the subjects and no opportunity for real-time adjustment. Transcripts of readings were randomly assigned to participants, who were asked to judge whether the text applied to them. The perceived accuracy became indistinguishable from chance. Another factor emerged: selective memory. Subjects remembered statements that seemed accurate and forgot those that did not. Ambiguous phrases were unconsciously reinterpreted to fit personal narratives. What initially appeared as precise insight was often a retrospective reconstruction shaped by expectation. As experimental rigor increased, the reproducibility of cold reading effects declined. Laboratories attempting to replicate earlier positive results failed. When methodological flaws were corrected, the phenomena disappeared entirely. The same readers who impressed audiences under loose conditions produced no statistically significant results under controlled testing. Importantly, this collapse did not imply deception in every case. Many practitioners believed sincerely in their abilities. The effectiveness of cold reading lies not in dishonesty, but in human cognition. People seek patterns, meaning, and validation. When statements align even loosely with personal experience, the mind completes the picture. Cold reading experiments occupy a unique position among irreproducible discoveries. The original observations were real in the sense that subjects genuinely experienced the readings as accurate. What failed was not the experience, but the interpretation of its cause. Once understood, the phenomenon ceased to function as evidence. Without interaction, feedback, and expectation, the apparent psychic ability vanished. What remained was a demonstration of psychological dynamics rather than a violation of natural law. The scientific response was quiet but decisive. Cold reading was reclassified from anomalous cognition to a social and cognitive process. The experiments did not disprove psychic claims through confrontation. They dissolved them through structure. Cold reading reminds us that reproducibility is not limited to instruments and measurements. It applies equally to human perception. When a phenomenon depends on belief, context, and interpretation, it cannot survive repetition under control. What once appeared extraordinary becomes ordinary the moment its conditions are fully understood. The opera Faster-than-light Neutrinos. In September 2011, a quiet announcement sent a tremor through the foundations of modern physics. A collaboration of scientists working on the opera experiment reported that neutrinos appeared to be arriving at their detector slightly earlier than expected. The difference was small, only tens of nanoseconds, but the implication was enormous. If correct, it suggested that neutrinos were traveling faster than light. The opera experiment was designed to study neutrino oscillations, not to challenge relativity. Neutrinos were generated at CERN near Geneva and sent through Earth's crust to a detector located deep underground at the Gran Sasso Laboratory in Italy. The distance between source and detector was precisely known, and the timing systems were synchronized using advanced GPS technology. Over several years, opera recorded thousands of neutrino events. When the data were analyzed, a consistent discrepancy emerged. Neutrinos appeared to arrive earlier than light would over the same distance. The result persisted across multiple runs and statistical checks. Cautious but unsettled, the team released their findings to the scientific community, emphasizing the need for independent verification. The response was immediate. Relativity had withstood a century of experimental tests. A genuine violation would require either new physics or a profound reinterpretation of existing theory. Yet the opera collaboration did not claim discovery. Instead, they invited scrutiny, openly acknowledging that an unknown systematic error could be responsible. Replication efforts began at once. Other neutrino experiments examined their own data. Theoretical physicists explored possible explanations, many of which required exotic assumptions. Meanwhile, opera scientists re-examined every component of their measurement system. As the investigation deepened, attention turned to the experiment's infrastructure. The precision required was extreme. Measuring nanosecond differences over hundreds of kilometers left no margin for unnoticed error. Each cable, oscillator, and synchronization module became a suspect. In early 2012, the source was identified. A loose fiber optic cable connecting a GPS receiver to the timing system introduced a delay in the synchronization signal. At the same time, an oscillator used for timestamping events was slightly miscalibrated in the opposite direction. Together, these effects produced the illusion of faster-than-light travel. Once corrected, the anomaly vanished. Subsequent measurements showed neutrinos traveling at speeds consistent with the speed of light, exactly as predicted by relativity. Independent experiments confirmed the corrected results. The faster-than-light neutrinos could not be reproduced. The opera episode did not end in embarrassment. Instead, it became a demonstration of scientific integrity. The collaboration reported their findings transparently, accepted criticism, and actively sought disproof. The error was found not through dismissal, but through repetition and scrutiny. Unlike hoaxes or self-deception, the opera anomaly arose from the limits of precision. The equipment performed almost perfectly, but not perfectly enough. At such scales, minor technical imperfections can mimic fundamental breakthroughs. The legacy of opera is subtle but important. It showed how science handles claims that threaten established theory. Extraordinary results were not embraced or rejected on authority alone. They were tested until the truth emerged. The faster-than-light neutrinos were never a discovery. They were a measurement artifact revealed by repetition. In failing to be reproduced, they reaffirmed a central principle of science. When results cannot survive independent verification, they dissolve not with drama, but with clarity. The Piltdown Man. In the early years of the 20th century, the search for human origins carried both scientific urgency and national pride. Fossil discoveries were reshaping the understanding of evolution, yet large gaps remained in the human lineage. It was during this period of uncertainty that the Piltdown Man entered the scientific record, not as a marginal curiosity, but as a central piece of evidence. In 1912, Charles Dawson, an amateur archaeologist, announced the discovery of fossil fragments in a gravel pit near Piltdown, England. The remains included parts of a human-like skull and a jawbone that appeared distinctly ape-like. Together, they suggested a creature with a large brain and primitive facial features, a combination that fit prevailing expectations about early human evolution. The find was presented to the scientific community with considerable confidence. Prominent anatomists examined the fossils and confirmed their apparent significance. The Piltdown Man was quickly accepted as a genuine early human ancestor, later named Ioanthropus dawsoni. For decades, it occupied a central position in evolutionary diagrams and textbooks. The appeal of Piltdown lay not only in its form, but in its location. At a time when major human fossils were being found in Africa and Asia, Piltdown placed England at the heart of human origins. This geographic implication subtly reinforced its acceptance, even as inconsistencies lingered. As more fossils were discovered elsewhere, questions began to emerge. Other early human remains showed smaller brains and more human-like jaws, contradicting the Piltdown model. Yet Piltdown was treated as an exception rather than an error. Its unique features were explained away as evolutionary diversity. Attempts to find similar fossils in the Piltdown region failed. No comparable remains appeared, despite extensive searching. Still, the original specimen remained unquestioned, protected by authority and tradition. The turning point came after World War II, when new dating techniques were developed. Chemical analysis revealed that the skull fragments and jawbone were of different ages. Further testing showed that the jaw belonged to an orangutan, artificially stained and modified to resemble human wear. The teeth had been deliberately filed down. By 1953, the conclusion was unavoidable. The Piltdown Man was a deliberate forgery. Whether Dawson acted alone or with assistance remains uncertain, but the deception had succeeded for over 40 years. The exposure of the hoax forced a painful reassessment. Entire lines of evolutionary reasoning had been built around an artifact that could not be reproduced because it had never existed in nature. The absence of similar fossils was no longer a mystery. There had been nothing to find. Piltdown did lasting damage. It delayed acceptance of genuine discoveries and distorted interpretations of human evolution. Yet it also strengthened scientific standards. Greater emphasis was placed on reproducibility, dating methods, and skepticism toward isolated finds. The Piltdown Man endures as one of the most consequential irreproducible discoveries in history. This failure was not technical, but ethical. It reminds us that science depends not only on method, but on trust. When that trust is broken, repetition becomes impossible, and truth eventually reasserts itself. The Mozart Effect. In the early 1990s, a modest psychological experiment unexpectedly entered popular culture and reshaped public ideas about intelligence. The Mozart Effect did not begin as a bold claim or a sweeping theory. It emerged quietly from a small study exploring how short-term exposure to music might influence spatial reasoning. What followed was not a scientific breakthrough, but a powerful example of how limited results can transform into widely accepted belief. The original study reported that college students performed slightly better on certain spatial tasks after listening to a short piece of music by Wolfgang Amadeus Mozart. The improvement was brief, lasting only minutes, and applied to a narrow type of cognitive performance. The authors made no claims about long-term intelligence or general mental enhancement. Despite these limitations, the findings attracted attention. Music, particularly classical music, already carried cultural associations with refinement and intellect. The idea that simply listening could increase intelligence resonated strongly. Media coverage amplified the results, often omitting critical details about duration, scope, and effect size. As the Mozart Effect entered public discourse, its meaning shifted. The temporary enhancement of spatial reasoning became, in popular interpretation, a general boost to intelligence. Products appeared promising cognitive development through classical music exposure. Educational policies were influenced. The original context of the experiment receded behind a simplified narrative. Within the scientific community, replication efforts began. Psychologists attempted to reproduce the effect using similar experimental designs. Some studies reported small improvements, while others found no effect at all. When effects appeared, they were inconsistent and sensitive to experimental conditions. Closer analysis revealed an alternative explanation. Listening to music can increase arousal and mood, temporarily enhancing performance on certain tasks. This effect was not unique to Mozart or classical music. Other forms of music or even engaging activities produced similar results. The observed improvement was not musical in origin, but emotional and physiological. When experiments controlled for arousal and enjoyment, the Mozart effect diminished or vanished. The performance gains were brief and task-specific. Long-term changes in intelligence were not observed. Over time, the effect failed to meet the standard of reproducibility required for a robust scientific finding. The Mozart effect did not collapse abruptly. Instead, it gradually returned to its original scale, a minor, context-dependent observation. The larger claims persisted in public belief long after scientific interest faded. The gap between evidence and interpretation widened. This case illustrates a subtle form of irreproducibility. The original effect existed, but its meaning was overstated. Replication did not eliminate the phenomenon entirely. It constrained it. What could not be reproduced was the broad claim that music fundamentally enhances intelligence. The Mozart effect remains a reminder that science operates within culture. When results align with appealing narratives, they can be magnified beyond their evidence. Reproducibility serves not only to confirm findings, but to limit them. In the end, listening to Mozart did not unlock hidden intelligence. It offered, at most, a fleeting moment of improved focus. What endured was not the effect itself, but the lesson it carried. When scientific findings escape their context, repetition becomes the only force capable of restoring proportion. Project Stargate Psychic Viewing. During the latter half of the Cold War, uncertainty itself became a strategic threat. Military planners feared not only weapons, but unknown capabilities, technologies or abilities that might exist beyond conventional understanding. It was within this atmosphere that Project Stargate took shape, not as an eccentric experiment, but as a classified intelligence program. Project Stargate was the culmination of a series of U.S. government-funded efforts beginning in the 1970s, aimed at investigating what was known as remote viewing. This term described the claimed ability of individuals to perceive distant locations, objects, or events using the mind alone, without sensory input. Reports suggested that trained participants could describe hidden military installations, geographic features, or sealed targets with surprising detail. The program operated under the oversight of military and intelligence agencies and involved researchers from academic institutions. Sessions followed a structured protocol. A remote viewer was given minimal information, often only coordinates or a coded reference, and asked to describe impressions, images, or sensations associated with a target. These descriptions were recorded and later compared to known data. Early reports appeared promising. Some transcripts contained elements that seemed to match real locations or objects. Evaluators highlighted instances of apparent accuracy, interpreting them as evidence that remote viewing might possess operational value. In an era defined by secrecy and rivalry, even weak signals were taken seriously. However, the structure of evaluation proved critical. Assessments often involved subjective interpretation. Descriptions were vague, symbolic, or metaphorical, allowing for flexible matching after the fact. When analysts knew the target details, unconscious bias influenced judgments of success. Hits were emphasized, misses quietly discounted. As the program matured, more rigorous testing was introduced. Blind and double-blind protocols were implemented to prevent information leakage. Independent judges evaluated transcripts without knowing target identities. Under these conditions, performance declined sharply. Statistical analyses revealed that results clustered around chance levels. Occasional correspondences occurred, but no consistent signal emerged. Attempts to train viewers to improve accuracy produced no reliable gains. Different viewers produced incompatible descriptions of the same target, undermining claims of objective perception. By the 1980s and early 1990s, skepticism within the intelligence community increased. Operational trials failed to demonstrate actionable intelligence that could not be obtained through conventional means. The costs of the program outweighed its uncertain benefits. In 1995, after decades of intermittent funding, Project Stargate was terminated. An independent review concluded that remote viewing had not demonstrated reproducible or operationally useful results. While some sessions appeared impressive in isolation, they could not withstand systematic evaluation. Project Stargate did not end in scandal. It ended quietly, as many irreproducible discoveries do. The data were declassified, and the program faded from institutional memory. What remained was a detailed record of how difficult it is to distinguish coincidence from capability when expectations are high and verification is complex. The failure of remote viewing was not due to lack of effort or seriousness. It failed because it could not be reliably repeated under controlled conditions. When stripped of narrative and interpretation, the phenomenon dissolved into statistical noise. Project Stargate stands as a reminder that even extraordinary resources cannot compensate for irreproducibility. In science and intelligence alike, belief is not enough. Without consistent results that survive repetition, claims, no matter how intriguing, remain unproven. The Benveniste Homeopathy Experiments. The Benveniste Homeopathy experiments occupy a rare and delicate position in modern scientific history. Unlike many irreproducible claims that emerged on the fringes of research, these experiments entered the scientific record through one of the world's most respected journals. Their rise and collapse unfolded slowly, under intense scrutiny, revealing how fragile extraordinary claims become when repetition is enforced. In the late 1980s, French immunologist Jacques Benveniste was studying allergic responses in biological systems. His research focused on how antibodies interacted with immune cells, a well-established area of experimental biology. During this work, Benveniste and his team reported something unexpected. Solutions diluted far beyond the point where any molecules of the original substance should remain appeared to trigger biological responses. According to conventional chemistry, such dilutions should be inert. Once a solution is diluted past a certain threshold, no physical trace of the original substance can exist. Benveniste's results suggested otherwise. He proposed that the solvent, water, retained some form of information about substances that had once been dissolved within it. This claim closely aligned with the core principle of homeopathy. The experiments were published in Nature in 1988, accompanied by an unprecedented editorial note. The journal explicitly expressed skepticism and stated that the findings required independent verification. This unusual step signaled both the potential significance of the claim and the editor's concern about its plausibility. The reaction was immediate. Laboratories around the world attempted to replicate the experiments. Initial reports were inconsistent. Some groups claimed to observe weak effects, while others reported none at all. The variability raised concerns about experimental design and statistical interpretation. To address these concerns, a supervised replication was organized. Investigators introduced strict controls, including blind and double-blind protocols. Researchers conducting the experiments were no longer aware of which samples were supposedly active. Under these conditions, the reported effects disappeared. Statistical analysis showed that the original results could be explained by random variation combined with procedural flexibility. Small changes in methodology produced large shifts in outcome. Without knowledge of sample identity, the biological responses fell to chance levels. Benveniste challenged these conclusions, arguing that the phenomenon was sensitive to experimental context and could not be captured by conventional controls. He suggested that intention, timing, and subtle environmental factors played a role. These explanations, however, moved the claim further from testable science. Subsequent investigations failed to restore the original findings. Independent teams using refined protocols found no evidence supporting water memory or biological effects at extreme dilutions. Over time, funding diminished, and the experiments ceased to attract mainstream scientific attention. The Benveniste experiments did not collapse because they were mocked or ignored. They collapsed because they could not be reproduced when bias was removed. The initial excitement was replaced by silence, as repetition failed to confirm the claim. This episode reinforced a central principle of scientific practice. Publication, prestige, and statistical significance are not endpoints. They are invitations to replication. When results cannot survive that process, they lose their status as evidence. Today, the Benveniste homeopathy experiments are remembered not for what they claim to prove, but for what they revealed about methodology, bias, and the necessity of skepticism. They demonstrate that even carefully conducted experiments can mislead when extraordinary claims outrun reproducible evidence. In the end, the experiments did not validate homeopathy. They clarified the boundary between observation and interpretation. Without consistent repetition, even the most intriguing results dissolve, leaving behind a record of a discovery that could not be reproduced. The Taos Hum. In the early 1990s, a quiet disturbance began to surface in the high desert of northern New Mexico. It was not visible, measurable, or easily described. Residents of the small town of Taos reported hearing a persistent low-frequency sound, often compared to a distant engine or an idling diesel truck. The sound was subtle but relentless, present mostly at night, and impossible to ignore for those who perceived it. The phenomenon became known as the Taos Hum. What made it unusual was not only the sound itself, but its selectivity. Only a small percentage of the population reported hearing it. Those who did described it with remarkable consistency, yet instruments placed in the area detected nothing abnormal. The hum appeared to exist without a source. As reports accumulated, local authorities and researchers took notice. Scientific teams conducted surveys, documenting when and where the hum was heard. Patterns emerged. The sound was often described as directional, low-pitched, and intrusive. It interfered with sleep, concentration, and emotional well-being. Some individuals reported physical sensations accompanying the noise, including pressure or vibration. Despite these accounts, environmental measurements failed to identify a cause. Sensitive microphones, seismic detectors, and electromagnetic sensors recorded no consistent signals corresponding to the reported experiences. Industrial sources were investigated and ruled out. Geological explanations were considered but lacked supporting evidence. The inability to capture the hum objectively became its defining feature. Without measurable data, replication was impossible. Researchers could not trigger the sound, isolate it, or observe it independently. The phenomenon existed only through testimony. Over time, hypotheses shifted toward human perception. Low-frequency sound can interact with the body in complex ways, and some frequencies lie near the threshold of hearing. Individual sensitivity varies widely. Psychological and physiological factors may amplify perception, especially in quiet environments where ambient noise is minimal. As investigations continued, the hum's geographic specificity blurred. Similar reports emerged from other regions around the world, each with its own variations. Yet none could be reliably recorded or reproduced under controlled conditions. The Taos Hum remained uniquely resistant to capture. Eventually, scientific interest waned. Without reproducible evidence, the phenomenon could not progress beyond description. For those affected, the hum was real and disruptive. For science, it remained unverified. The Taos Hum occupies a subtle space among irreproducible discoveries. It was not a false claim, nor a failed experiment. It was an experience that resisted objectification. Its reality depended on perception rather than measurement. In the end, the hum faded from attention, though not necessarily from memory. It left behind a reminder that not all phenomena submit easily to instruments. Yet without reproducibility, even persistent experiences cannot become scientific discoveries. The Taos Hum did not resolve into explanation or proof. It simply endured briefly, quietly, before slipping beyond the reach of verification, joining the long list of phenomena that could not be reproduced again. Ending. Some discoveries don't disappear because they were false, but because they couldn't be repeated. Without reproducibility, even the most fascinating ideas remain stories rather than knowledge. If you enjoyed this journey through science's unresolved moments, leave a like, subscribe to the channel, and share this video with your friends. Your comments help keep these conversations alive.